All right, so going back to this undesirable resonances that we have right here, now we can think about ways to mitigate this, this problem. So let's see whether we can make the impedance Z, in this case here, so small it doesn't interact with Zn or Zd. In this case here, since Z is open, we would want to make it as large as possible, really, to avoid interaction. So we have 1 plus Zn over Z over 1 plus Zn over Z, 1 plus Zd over Z. So you can say, well, if I could make magnitude of Z much larger than the magnitude of Zn or the magnitude of Zd, I would be just fine, right? That's one strategy. Is that possible? How would we make the magnitude of Z larger? Z is capacitance, right? So Z is 1 over SC1. So if you wanted to make the magnitude of Z larger, you can reduce the value of the capacitance. That would bring this up right here, and you're hoping that you can bring this up to high enough value so that that extra impedance becomes much larger than either Zn or Zd. Unfortunately, that's not going to work. No matter how large Z we make, we are not going to be able to avoid this interaction because, unfortunately, Zd and Zn are both inductive. As you go up in frequency, they are larger and larger. There's no way to remove that capacitance interaction with these inductances, except, of course, you know, in the limit, you can just take it out. But if you take it out, this converter no longer works, right? So this is just not going to be an option. You can't remove the interaction by making the impedance much, much larger than Zn or Zd. You know, if these factors were opposite, right, we would be talking about trying to make the impedance much smaller, right? So this, maybe I'm confusing you with what it should be much larger or it should be much smaller. In this case here, it should be much larger, but we conclude that we can't do it. So what is the other option that we have? You know, we go with this phase approach, right? We go with this. We want to go with this green box right here and make the phase to our favor. How do we do that? How do we make the interaction be such that it's not capacitance versus inductance? So would be great if we, instead of the capacitor, we had a resistor, right? If you just replace the capacitor with the resistor, that would be fantastic, right? We could have something like this. You know, let's suppose I'm going to put it here. Let's suppose right here. Okay, this is some resistance R. If our impedance, instead of the capacitance, were just a resistance, the interaction here and here would be just fine because we would have 90 degrees of phase shift, or around 90 degrees of phase shift, and the impact on the correction factor and thereby on the overall transfer function would be very small. So that's great, but of course in the SEPI converter, if you replace that capacitor with resistance, you know, the converter not only doesn't work, but even if it does work, in some sense, you're going to be dissipating power on that resistor, so it doesn't make sense. So we can, however, exploit this idea of trying to cross these impedances at a flat line and arranging what we call a damping network so that we preserve the properties of the SEPI converter normally operating, minimize the power loss, and yet, in this range of frequencies that we're looking at right now, make that extra impedance look resistive. Okay, so how do we do that? We start off with, you know, this is our extra element is C1. This is C1 right here. This is 1 over omega C1. And then we want to make that be resistive at a certain frequencies. So we can put a resistor in parallel with this. Let's call this RD. And then see what the response would actually look like. If you put RD in parallel with C1, how does the extra element impedance look like? I'm going to call this one RD right here. So you have RD is impedance of that extra resistor. 1 over omega C1 is the magnitude of the, the impedance of the C1. And you have parallel combination of these two. So remember the algebra on the graph type thing from the introductory class. What is the total impedance that we have right here? It's going to be the smaller of the two. Okay? Well, that's actually good news because now I can say I will follow this resistance R right here up to this point, and then I'm going to follow the 1 over omega C1 going forward. Would this be a good way to remove these interactions? Yes, it would, as long as I've picked my RD skillfully so that I produce this interaction right here. I'm crossing the Zn and Zd at a point where my parallel combination of RD and C1 looks resistive. Okay, so this is all great. This, in fact, is a good way to do the damping. What is not good about it? What is impractical about this particular approach? It's a power dissipation. You're going to have a DC voltage across this C1 in the SAPI converter. In fact, that voltage is going to be equal to the sum of the input voltage and the output voltage. Lots of DC voltage across that component, and then you place a resistance of RD in parallel with that, and you just dissipate power. It kills the converter, really. So to mitigate that, we realize that all we need to have is a resistive impedance right here, but it doesn't matter what happens right here. And so we can add an element in series with RD to remove the DC power dissipation and preserve the resistive property of that impedance in the range of frequencies we care about. So you can envision that that's going to be very simply consisting of adding a CD capacitor in series with RD. Okay. So what is going to be the impedance now of this combination when we add CD, and how should we choose the value of CD to produce that effect? We want to preserve this, right? This is the most important part of the damping. As you go up further in frequency, what is ultimately the asymptote of this combination going to be? C1. It's going to be just C1 because CD is in series with RD. At high frequencies, CD goes away. RD becomes much larger than C1. And so at high frequencies, you're going to be following exactly what we have already drawn. So that's all great. Now, at some point, we have to have this CD effect present. What happens at low frequencies with this network? How does it behave at low frequencies? So CD becomes much larger than RD, so it swamps RD. So in that series combination, you will have just CD, and then it's in parallel with C1. So at low frequencies, we have the behavior of a parallel combination of CD and C1. That parallel combination is impedance that is smaller, obviously, than C1, as it should be, and we position it to be like this. Okay, sorry. So like that, right? The same slope of minus 20 dB per decade. This is minus 20 dB per decade. And this here is the impedance of that damping network that we have added to produce these desirable effects. So you see now we have approximately 90 degrees type interaction. So small effect on the correction factors and thereby the transfer function of the converter. At high frequencies, this does still behave as a capacitor, and low frequencies, it does behave as a capacitor of larger value, right? So this here is going to be 1 over omega CD plus C1. So as you look into the assignment, you will see that you can exploit this discussion here to your advantage. So first of all, you want to find out what RD should be placed so that you have the desired interaction between the extra impedance and the ZD and ZN. Then you decide how large CD should be placed so that you have this nice range of frequencies right here where that interaction is, well, the impedance looks resistive. That's it. Okay? Any questions on this? This is one very standard, very common way of damping converters in general. You will see this coming up many different times, but here it's interpreted in the context of the extra element theorem, which is probably the best way to introduce that damping in the first place. Questions?
You said that you cannot, what happens if you take it really to high frequency instead of adding the C1? The C1, if you take it to really high frequency, that...
Right. So if you could do that, right? So if you take the C1 to very high frequencies, you will have unavoidably this interaction at higher frequency. Now that may be favorable, right? So having the interaction at higher frequency, going back to this response right here, moving this up in frequency certainly does help, right? You then have more room to work with before you hit that interaction. Practically speaking, remember, C1 is a part of a converter. You cannot arbitrarily reduce the value of C1 because then you're going to have increasing ripple across that C1. You will have then be facing the issue of whether you can find a component that has such a small value and enough current rating in terms of the RMS current and so on. So practically speaking, this approach of just trying to shift this up to higher frequency is good, but it has limits. And so normally you can only do it so much. You can do both, right? You can say, I'm going to reduce that capacitance value to something that I can find practically and have still reasonable ripple across it, and then damp it. And that's perfectly fine. So the combination of the two approaches is quite appropriate as well. Okay, any other question on this right here?
Can you please repeat how to choose RD?
How do you choose RD? So you see, you start with, let's suppose C1 is given, right? So C1 is right here. Now, if you choose RD to be right here, you see that you're not accomplishing anything, but you'll still be crossing ZN and ZD at the inductive versus capacitive interaction. So you have to have RD that is small enough, smaller than the impedance that you have right here. So RD has to be small enough in value so that the interaction here is avoided. So this flat line has to be below this point right here. There is some room here for not uniqueness, right? There's, I've picked this value right here somewhat. It's not arbitrary by any means, but it's somewhat arbitrary right here, right? So it's just less than this. And you can see when you do your assignment, what happens if you move this up closer to this interaction or if you move it further away from the interaction. Okay.
So you can also place it above the dot, right? So then the Q factor just becomes equal to the value of RD. So
you could certainly, again, there is room here for playing with these components, and you can move this up and say, I'm just going to cross right here exactly and see what happens, right? So it is a matter of what we would call optimum damping. Leave that question for a little bit later when we do the input filter design. We'll actually address this in significant detail. There are closed form expressions for how to do the damping in the optimum sense. But right now, let's leave it as something that you can play with a little bit. Yes?
So when you say it's damping, are you implying that you always have to add a resistor?
When we say damping, we imply that we have to add a resistor. That's pretty much it, yes. So now you can see here that adding this resistor right here is going to have some effect on the loss. Why would it have an effect on the loss? Because the voltage across the capacitor C1 is not exactly DC. So ripple voltage across the capacitor C1 is going to be, presumably this one is large enough that ripple is going to be visible across RD. And so there is going to be some extra, in fact, loss associated with this network. The loss is going to be small as long as the ripple component of the voltage across C1 is small. The closer the voltage across C1 is to DC, the less dissipation you're going to see on RD.
Another alternative is that one can add an inductor in parallel so that it also looks inductive as ZD. And in that way, the converter doesn't work, right?
If you put the inductor in parallel right here?
Yeah, and you have no phase, they are both inductive. So
yeah, but just putting an inductor in parallel with the C1 is going to be a DC short, so that's going to totally destroy the converter. Okay.
So in Z in and ZD plot, there is like this thing, low frequency. So R should be chosen so that you avoid that region.
Yeah, you may have some issues right here, right? If you know, there are more complexities here than we have explained so far. It is possible to choose things so that you hit now a different type of interaction right here. So we want to stay away from that if we can. Okay. All right. Now let's see what happens when we put inside this inside the circuit. So here is that damping network, fairly common, by the way, in the SEPIC or TUC type design. Things actually get a little bit better further when you include ESR of the capacitors. That also tends to damp the resonances somewhat, but you don't want to really count on ESR to solve your problem. This is a systematic way of really solving that issue. And this is the kind of a hand asymptote sketch of the design of that damping network. You know, positioning RB to have this 90 degrees type interaction right here. And we already explained that, so probably no need to spend more time here. Notice the value of the RB, the damping resistance, here is in the order of few ohms for this particular example. So here is the damping. I used RD, it's the same thing. And so the damping network placed. And the results are here shown on the right-hand side. You see the magnitude and phase responses of GVD-BB. This is without capacitor C1. And GVD, that's the solid line that's with the damped capacitor C1. And you see that we have removed these resonances entirely. It's in fact difficult to even see that these two are different transfer functions. And similarly, in the phase responses, we have finally the asymptote of minus 270 degrees. So we have removed the right half plane zeros. And so we will have a pair of zeros that are well damped, a pair of poles that are well damped. They are at the frequencies that are close to each other. So the net effect of the entire correction factor is very small. So this looks good. So this is in the end what you want to see when you check whether you've damped the circuit well or not. Okay, so summary on the extra element theorem. So it's a design-oriented technique that allows us to write the system transfer function in terms of the system transfer function without an impedance that we consider extra. And there are two cases where we consider that impedance as an open or as a short. And the transfer function is written in terms of the correction factor that depends on the impedances ZD and ZN that are seen at the port where the impedance Z is connected. And then we have looked through several examples of practical applications. One is to just simplify analysis. That's great. Evaluate the impact of a parasitic element on that was not included in the original design, such as ESR of a capacitor. And then finally, maybe the most important part is that we can establish conditions for this extra element impedance to not affect us, or to design the impedance so that it doesn't affect us. To damp the resonances is a good example of that.